Now we have to study the equation of motion of the center of mass. Equation of motion. What is the equation which governs the motion of center of mass? Last lecture we saw that it's enough to just study the motion of center of mass if I want to study the overall motion of the system as a whole, right? So let's try to see the equation of motion of the center of mass. So for this, let me consider a system of n particles, m1, m2, mi, mn, and whose positions are described by, whose positions are described by the vectors, position vectors, say r1, r2, ri, rn. The position vectors are described by r1, r2, r3, ri, rn, right? So let me draw it. Let me draw this. Oh, sorry. These are the system of particles m1, m2, m3, m4, mi, mn, and their positions are described by r1, r2, r3, ri, rn. So if I want to write the equation of motion of each particle, then this will be m1 r1 double dot equals to, I can write f1 ext, f12, f13, f1i, f1n, and mass into acceleration of the second particle is f2 external, f21. What is f12? What is f1 external? F1 external is external force acting on m1. External force, the force which is not applied by all these particles, is by something outside the system. Force is someone outside the system apply on m1. These particles are belonging to the system. So force which they apply among themselves is the internal force, like f12. F12 is a force applied by 2 on 1. F13 is force applied by 3 on 1. F1i is force applied by I on 1, and F1n is force applied by n on 1. So these particles, when apply force on m1, they are internal forces because they are the forces applied by fellow particles, right? If some particle is applying force on m1 from outside, there is some particle outside the system and is applying force on m1, that's going to be called external force, that is f1 ext. You may have more than one external forces, so I'm clubbing them all and putting f1 external over here. Similarly, f2 external, f23, f2i, f2n, and similarly I can write equation of motion for ith particle. So that will give me fi external, fi1, fi2, and this will be fi I minus 1 plus fi I plus 1 plus fin. Similarly, nth particle, I write fn ext, fn1, and this is fn2 and this will be Fn minus 1. Right, so these are the equation of motion. You can see yourself how difficult these equations are, right? Or actually most of these forces will be 0, but even then this is not very easy. If I want to study the motion system as a whole, then I'll devise some way so that I don't have to solve these complicated equations, right? The equation has to be solved when you are interested in motion of individual particles. When you are interested in motion of individual particles, there is no other way. You have to solve this equation and get how m1, m2, mi, mn are moving. But right now I am interested in motion of system as a whole. I am interested in motion of the system as a whole. So if I write this equation can be written as mi ri is FIEXT plus, I write sigma Fij j varying from 1 to n except j equal to I. Okay, if I sum all these equations, so what I'll get is sigma mi ri equals to sigma FIEXT plus sigma Fij and j not equal to I. J not equal to I. I and j are going to vary from 1 to n except j not equal to I, except j equal to I in fact. So what are these forces? These are internal forces. For every F12 there is F21. For every F13 there is F31. So every Fij there is Fji. For every Fij there exists Fji such that Fij is minus of Fji. Fij is minus of Fji. So this term is going to cancel out, right? There will be action-reaction pair. There will be always an action-reaction pair. So our equation comes to be sigma mi ri equal to sigma FIEXT, or this can be written as sigma mi ri upon sigma mi equals to sigma FIEXT. Sigma mi is total mass of the system. I can call it m. Now I define RCM equals to sigma ri mi upon sigma mi, and let me write FEXT. This is the net external force acting on the system. So this becomes how much? M RCM double dot is equal to F external. So this is going to be very, very important equation. Whereas M is this, right, and FEXT is this. So this is very important. See, this is important. This is telling you what? This is giving you how the center of mass is going to move, how RCM is going to vary, how the center of mass is going to move in space, how center of mass is going to vary with time. This equation is the equation of motion of center of mass. Equation of motion of the center of mass. This is the equation of motion of a single particle whose mass is capital M. Let me draw it. This is equation of motion. Say you have a particle over here and that very important particle is capital M, that is center of mass. So instead of studying the motion of all these particles, I'll just concentrate my energy on this. I'll concentrate my effort on studying this particle who is having the mass capital M and the positions given by RCM, and the force acting on this particle is net external force acting on the system. So instead of, I'll just concentrate on just study this particle. Has the got mass M? Just study this particle, say mass M, and the force acting on it is Fext. So this is equation of motion of a particle whose whose mass is capital M and the positions given by RCM and net external forces Fext, right? So this will help you find out how the position of the center of mass is varying with time, and once you get this motion of center of mass, the overall system will be here and there about that center of mass itself. So this is the equation of motion of center of mass. Okay, this is the equation of motion of the center of mass. We write it as mRCM equals to F external. Now let's do some analysis. Suppose if F external is 0, it means what? RCM double dot, which is nothing but acceleration of the center of mass, is 0. It means VCM is constant. When VCM is constant, I can say VCM is constant. It means when ACM is 0, VCM is constant. It means velocity of center of mass is constant. And if at any time VCM is 0, then it means that VCM is constant with time means if at any time VCM is 0, VCM will always remain 0. VCM will always remain 0, and when VCM is 0, your RCM is constant. VCM is 0, your RCM is constant. Means if net external force is 0, means VCM is constant. If at any time or in some frame, if suppose VCM is 0, constant can be 0 also, then in that case the center of mass is not going to change, right? This is extremely important while solving problems. Many times what we do is your Fext, net force Fext as a vector quantity may not be 0, but one of its component may be 0. Like say, if suppose Fext can be written as Fxi, Fyj and Fzk, then this vector equation reduces to MACMX, center of mass, acceleration of center of mass in x direction, x component of the acceleration of center of mass, ACMX is Fx, and MACMY is Fy, Fz. Now if suppose your net force is not 0, but one of its components is 0, in that case ACMX is 0, and then you can write VCMX is constant. And if at any time, then VCMX will be 0 always, and I can write XCM is constant. XCM is constant. What is XCM? XCM is the x component of the position of center of mass, that is XCMI, YCMZ and ZCMK. right? Similarly, I can say for this also, if Fy is 0, ACMY is 0, and VCMY will be constant. If at any time VCMY is 0, then at every time VCMY will be 0 and YCM will be constant. Similarly for ZCM also. So these are very important. These are very important. You don't remain confused in that if Fx is 0, RCM will be constant. No, it's VCM which is constant. It's VCM which is constant. So this analysis will help us in solving numerical. Now in the next lecture, I'll be telling you how to compute the positional center of mass. That is one of my lecture that I prepared for mathematics students, right? So I'm giving you the same lecture in next time. In next lecture, you'll be having a video which I prepared for mathematics student, right? So please see to it. That will help you how to compute center of mass and how does center of mass depends on symmetry, right? So thank you very much.